The purpose of the presentation was to a master's class for renewable energy systems, and the idea was to give an industry perspective. So what I decided to do was talk about what I do, what are the issues that affect those areas, what I'm reading at the moment, what are my perspectives about what's going on, give a bit of a perspective on storage because of projects I'm involved in, and then a bit of a big overview on where we're all going, and is where we're going or trying to go, is it possible? This is a well-used slide from the 2020 Integrated System Plan by AEMO, and this is their step change. So this is effectively one of their fastest change scenarios in the model, and it requires about 3 gigawatt of new renewables to be added between now and 2042, added each year. So here we are with the grid at the moment, the NEM, the National Electricity Market, around about 70 gigawatts of generation, and the colours, you can see the individual colours on the legend down the bottom. And what the step change does is effectively double that. So it doubles it up to 140,000 by 2041-42. And that gets us to around about 95 to 97% renewable energy as a percentage of the total at that point. So you'll see down the bottom, there's a really tiny amount of what could be coal or it could be gas. Obviously in 20 years, there's many opportunities to change that or look at biofuels or hydrogen. A lot of things can change over that 20-year period. A really important part of this graph, which a lot of people often don't highlight, is this red dotted line. So one of the issues that we get talking about a lot is, so as we go to intermittent variable renewable energy, will we lose the ability for AEMO to turn the knob up or turn the knob down on dispatchable energy? And what the red line shows you way back now in 2021-22 is that we have about 40 gigawatts of dispatchable energy right now, made up of black and brown coal and hydro and gas, for example. What the red line you see is, as we go forward for the next 20 years, is it doesn't really change much. So the idea is we replace the gas and the coal and we add storage, and the storage can be pumped hydro or batteries or even hydrogen. And so the idea is we maintain this level of around about 40 gigawatts of energy right through. And that's an important thing which answers the question to people who say, but how can we survive in an intermittent, variable, renewable grid in the future? And you can talk about that for an awful lot, about different aspects of it. In terms of what storage would be needed, again, because I have a storage focus in the work I do, as I said, the step change scenario is for 96% renewables in 2042. And this is the amount of storage that would be required. And yes, it is a lot of storage. So this is where we need to differentiate between the megawatts and the megawatt hour. In other words, how many megawatts of actual storage needs to be connected at that point in time. And so out of that 40,000 megawatts or 40 gigawatts of dispatchable that was shown in the red line on the previous chart, this step change scenario has us with just over 20 gigawatts of storage. So it's not all batteries. This also includes pumped hydro, and it could even potentially include hydrogen and other storage mechanisms. And so just looking at that 20 gigawatts in 2042, you'll see it's actually fairly even in the 4 different categories. So the purple at the top being behind the meter, so in houses and businesses, and then deep storage is the next one below that. So that's a sort of our pumped hydro energy systems that can last for around a week, certainly for 24 hours to a week in duration. Then the medium level storage is the next one down, again around about 5 gigawatts, and that is 4 to 12 hours, for example. And then the lowest one of the lot, which is the shallow storage, is your typical lithium ion that you're seeing at the moment, which is generally a 1 to 2 hour storage. And when you add all of those up and then look at how many times they will discharge over the year. Each one has a different number of cycles per year that it would go through. And the really deep ones, like the pumped hydro Snowy 2 scheme being put in at the moment, they would only fully cycle something like 15 times a year. But your short duration 1 to 2 hour lithium ion, you'll see that that's cycling nearly every day. And so doing arbitrage or frequency control, for example. Then the actual volume of storage. So if a 1 megawatt battery runs for 1 hour, then it's a 1 megawatt hour battery. If it has 2 hours of storage, but still only 1 megawatt connection to the grid, then it's a 2 megawatt hour battery, but it only has 1 megawatt of this area down here, 1 megawatt of connection capacity, but it might be 2 megawatt hour of actual capacity. So as the megawatt hour goes out into 10 hours to 20 hours, for example, or a week, then you're getting a lot more megawatt hours than you are the megawatts of that particular battery. One of the jobs I have is I work for Sumitomo Electric Industries as an Australian energy market advisor, and this is their flow battery. So the flow battery is, as it sounds, it uses liquid electrolytes. If you look over here on the top right picture, you've got 2 tanks down the bottom. One is the positive electrolyte and one is the negative electrolyte. And then they flow through this membrane system up the top to produce electricity. And so if you want more and more megawatt hours, you just have more and more tanks. Whereas the actual megawatt connection size is determined by this cell stack at the top. And so you see that down in the picture on the bottom right. If you've got 20-foot tanks down the bottom, then the battery will have 3 hours of duration, 30-foot tank 4.5 hours, and 40-foot tanks 6 hours. As you can see, we've used the international standard sizes here for containers, which means these can all be built in a factory on an assembly line and moved to site. The biggest battery that Sumitomo ever made, and in fact it was for a short period of time the world's largest battery before the Hornsdale Power Reserve was built in South Australia, is this one on the bottom left. It was a bespoke design, so it was all manually assembled inside a very large building, and so it has these individual tanks on the ground floor, and then these cell stacks that you see in the very bottom of the picture, which were then on the second floor. So it's a very large version of what you see up on the right, which is only a 250 kilowatt battery, and this one down here was a 15 megawatt battery that could operate for 4 hours. Hence it was a 60 megawatt hour battery. Some of the issues for Sumitomo Electric Industries for our vanadium redox flow battery, it was invented here in Australia, which is a wonderful story, by University New South Wales. And its smallest size though is those 3 shipping containers I showed you on the previous picture. And so that's 750 kilowatt hours, which is 250 kilowatts by 3 hours. And then they can also be 4.5 or 6 hours. The things against flow batteries is they have a higher capex, so can be 50 to 100% higher depending on the configuration, and they have a lower efficiency. So the cycle efficiency, AC to AC, is something around 72% rather than in the high 80s for lithium ion shorter duration batteries. The big positives are that they have a long life. So we sell them with a 20+ year performance warranty period. Minimal degradation over that period compared to lithium ion, which can degrade quite a lot over that a 10+ year period. Unlimited cycling, which is good if you're wanting to chase lots of frequency control services, or you just want to cycle it for some reason, perhaps twice a day instead of once a day. So it means for unlimited for those 20 years. Also, there's no thermal cycling limits. Because there's so much thermal inertia in the liquid electrolyte, you can push it quite hard chasing FCAS services, and you don't get any individual cell temperature issues in doing that. So you can do that sort of all day if you wanted to. It's also a very sustainable electrolyte, the vanadium. It can be mined, refined and manufactured here in Australia. There's 3 potential mines ready to go in Australia if they can get downstream service agreements, sale agreements, and it doesn't degrade the electrolyte in the battery. So after 20 years, when the electronics is getting old, you could take it out and put it in another battery, or you could remove the vanadium out of the electrolyte liquid and send it off to the reinforcing steel sector, which is where most of vanadium goes at the moment. The other wonderful thing is that it's non-combustible. It's a liquid that would put out a fire if the battery leaked for some reason. And so for all of those reasons above, it's probably more suited to utilities who are quite comfortable in buying 50-year life assets rather than 10-year life assets, for example. My other part-time job is with Yarra Energy Foundation, and this is just a little bit of an overview about what we do in the Yarra Energy Foundation. The 2 big things that we're facing the community with at the moment are our Metropolitan Community Power Hub project, which started this year in 2021, and also the Community Batteries project, which has started this year in 2021. The Community Power Hub was an initiative of the Victorian Government and facilitated via a grant from Sustainability Victoria. We've already got over 10 groups on board connected into that Community Power Hub. It's like a network of community energy groups and interest groups, and we've got 3 staff working on that. So we've added some new staff, which is great. The other project is the Community Battery project for a community battery in the City of Yarra area. Again, that was from a Victorian Government grant. We were one of 19 grants issued by Victorian Government, and one of the 3 which received a CapEx grant. The project is for around about a 250 kilowatt hour battery, and it would be low voltage connected to the street wires, so to the 400 volt, 230 volt wires in the street. Our partners in that project are City Power and also the Australian National University, who are helping us with the software. Software is a very important point of this project. So you'll often get confused in people talking about battery system software, and you'll hear the terms BMS, PCS and EMS. So BMS is the battery management system that protects the battery, looks after it, makes sure nobody tries to do anything which would upset the battery. And so that comes with the battery from the battery supplier. The PCS is the system that looks after the inverter and rectifier unit, where the AC is converted to DC and the DC can be converted to AC when you're exporting. And so that will come with the inverter package, which is usually a different company than the company that's supplying the battery itself. And then a battery supplier will often combine those 2 together. But the third part of the software, the EMS, is the energy management system, which is much, much harder to buy from a third party. There are systems around, and in this particular case, we've decided to go and dedicate a group to write our own EMS system, and that will be the work done by the ANU, their grid team there. The idea of this model is to use both retailers and an aggregator in conjunction with the customers. The individual customers connected to the battery and using the output from the battery would be doing that via their retailer, a retailer who's got involved in the project with us. And then the grid services that we can sell from the battery back up into the grid to the distributor and retailers and others will be through an aggregator. And so that's maybe a different retailer. The idea of the project is to determine the commercial model. So at the end of it, at the end of next year, for example, have we determined that we've got a commercial model? And then if we have, we can then go out and repeat that perhaps 50 to 200 times. So that's the aim of that particular project. I also have another part-time role, which is working as the secretary for the Australian Institute of Energy and the Victoria branch. So this is a role I've had for quite a while, and we've been doing some really interesting things this year. This initiative, which is shown on this slide this year, was a series of programs for emerging energy leaders. This is probably one of the best things that we've done over the last decade. And the idea is to identify emerging energy leaders in Australia and help to coach them and mentor them through a program so that we end up with very capable and fit for purpose energy leaders in Australia in the future. So having better and better energy leaders. This has been a really great program. The AIE is a 42-year-old association. And one of the other things we do, which I enjoy, is we have a postgraduate energy poster competition, which we run every 2 years and have for about 3 decades. And University of Melbourne has been a sponsor of that for the last couple of times we've done that, which is wonderful. In 2020, we had to go virtual because of COVID, and the All Energy exhibition and conference was closed. So all of the posters and entries are still online and available to have a look at. And as I said, the Emerging Energy Leadership Program, we ran 5 events, and these are some snapshots of those 5 events that we ran this year in 2021. Whenever I get a group stuck in front of me, I like to go through this policy slide. Apologies, I just had to close the door. We'd like to go through this policy slide and talk about what the way policy is supposed to be developed. So this is a technical description, and it's what you'll learn if you're doing a university or other course on public policy development. I'm not going to go through it, but obviously this is the proper way to do policy when you go through it in a methodical and process way. However, it's not the way that policy is always done. So policy is often done on the fly, and even though our ideal for policy is to have a public policy informed by rigorously established objective evidence. In other words, you do your research, you evaluate, you determine what the policy is, you evaluate that, and then you actually roll it out, implement it, evaluate it, and then adjust it. But sometimes election policy just happens all of a sudden. Prior to an election, parties can come up with ideas and they haven't gone through all that rigorous process. Or you can even get it through tweeting. As we saw with the gentleman in this picture on the left, who hopefully you'll know is Mike Cannon-Brookes of Elysian, and we had policy that started with tweets being swapped between Mike and Elon Musk, and that ended up in the largest battery in the world, of course. The Hornsdale Power Reserve in South Australia was the largest when it was put in, and that was all done publicly in a series of tweets over 24 hours, and all of a sudden large-scale grid batteries were launched as a policy in Australia. So we call that policy-based evidence making, where we go back later and work out, was that a good idea and how did it work? One of the other things I like to highlight when I'm talking about this is that it is generally hard for a policy to achieve more than one outcome. So a single policy achieving multiple outcomes. We might want to make energy more reliable. We might want to make energy greener, but we also want to get economic development, investment, jobs, etc. And so sometimes we try far too hard to get one policy to do multiple things, and it often doesn't work. A bit of an overview for the NEM and how does it work in Australia, our national electricity market. You've probably seen this diagram before, but it just indicates how all of it works. So we have this thing at the very top called the Energy National Cabinet Reform Committee. Used to be a very public process. Unfortunately, that has turned into more of a secretive type committee, so much less is published about it than the old committee we used to have. And over on the top right there, you'll see that it's informed by the Energy Security Board, which came into being, I think, around about 6 years ago, and has recently just changed several of the officers. A lot of the work, of course, this Energy National Cabinet Reform Committee has the state and federal energy ministers in it. And so, of course, they don't go off and do all the work. So most of the work is, of course, physically done by on the top left there, the senior committee of officials. And so that's lots and lots of energy policy people from state and Commonwealth government who spend a lot of time talking to each other in between the National Cabinet Reform Committee meetings, which is sometimes as little as 2 a year. But the officers who work behind the scenes are constantly talking to each other, state to state and state to Commonwealth. So that's very important. And then the three very public bodies that we all know about are the Australian Energy Market Operator, AEMO. So they're the engineers who make sure that every second of every day, the electricity supply and demand are matched and balanced and keep the voltage and the frequency correct. In the middle, the AEMC. So they're our rule maker. They're the people that make all the rules, the regulations, the codes, the laws, and for everybody else to operate to. And then over on the far right, the Australian Energy Regulator. So they're like the police, effectively. So they make sure that everybody is following the rules which have been created, developed and published by the AEMC. And then down on the bottom, we've got all our market participants, which is the big ones, of course, are the ones that are actually buying and selling electricity from generators through to your retailer. But of course, even householders are a market participant in a different way. So when you're developing an energy policy, if you're sitting down as a government person and developing a policy, you ask yourself, what's the policy for? What are we actually trying to do? Are we trying to provide energy security, perhaps CO2 reduction, investment or economic? As I said before, it is much better to try and focus on a single item and have a single policy for that. But we often try as a government to do multiple things with the same policies. The other thing to be aware is that policies interact with each other. So sometimes a new policy comes out, which in isolation looks like a good idea, but it then interacts with other policies and causes things which we didn't think about at the time. Obviously, people developing the policy try hard not to do that, but sometimes it's an outcome. A really, really, really important thing is, are these policies predictable for business? What is it doing to the investment world? We've had, unfortunately, over the last 15 years, what we often call as the roller coaster of energy policies, which makes it really hard for businesses to invest. Businesses come up with great ideas. They want to implement them. Yes, they want to make money, but they need to then invest something, a project, a generator or transmission, for example. And they can't do that unless they can get funding. And they can't get funding unless the banks are happy to invest in those projects. And the banks are very nervous. The funders are very nervous. And they're the ones that will look at a wonderful project and say, well, that's a great idea, but we just don't think the policy certainty is there for this one. We're concerned that we might look at making money in the first few years, but will we make it for the 10 years, for example, that we need to see a return on their money? So that means, will the companies invest? And then even if they do invest, will they stay? So for example, we had a Vestas Energy Micron blade factory in Portland in Victoria over a decade ago. It was a great initiative. They got a grant, they invested, they built a blade factory, but then 2 years later they closed it. Similarly, Tasmania had a manufacturing hub for wind turbines and the wind sector, and that also didn't last for that long. So some of these ideas look like they'll have an outcome that is sustainable, and sometimes it's not. And I mentioned sometimes about how the outcomes of the policies aren't what we really intended. And so here's a good example. Here's my current electricity bill, which you'll see is about $800 in credit. And that's because of a thing called the premium feed-in tariff that came in. At the time, it may have seemed to some people like a good idea. A lot of us were concerned it was too much for too long, and that seems to have been borne out. There's an awful lot of people around who are still on this premium feed-in tariff and will be for another 3 years. Perhaps an example of a policy that wasn't properly thought out. Well, Australia's going through an energy transition. It would be hard not to be aware of that if you're living in Australia. And what is it? Well, it's a demand for an awful lot of energy storage, as I showed on that chart earlier in the presentation. And the whole energy transition, according to the Integrated System Plan, has a cost of over 200 billion in the next 20 years. It will effectively decarbonise Australia's electricity system, but only the electricity system, and I'll come back to that in a later slide. It will move us from having baseload coal power stations to variable baseload renewable generators in the system. It will replace effectively the 32 baseload coal power stations we've got by 2050, and 13 are already closed, and 8 more of those are expected to close by 2040. For such a massive thing, is there a plan? And the answer is sort of yes and no. So there is a plan called the Integrated System Plan, the ISP, and that gets updated every 2 years. But what a lot of people forget is that this is not a plan for decarbonisation. It's not even really a plan for generation in Australia or the way it's consumed. This is a transmission plan. This whole purpose of the Integrated System Plan is to work out what large transmission infrastructure we need in Australia and to make sure we're planning for it in time and then able to build it in time for when it will actually be needed. So remember that it's a transmission plan, not a decarbonisation plan. And so it's focused on the electricity sector. It looks out 20 years to 2042. And the good thing is it's repeated every 2 years. So the 2022 version is being done right now, and the draft will come out, we hope, in December of 2021. But there's a lot of other reading you need to do. The Integrated System Plan is very important and it's well worth reading, as is the draft in between when it comes out. But here's just a few of the other important outputs or reports which come out every year that are worth reading if you want to try and get a good understanding of how the national electricity market is going. The first one there is the Renewable Integration Study, which comes out from time to time, and it's looking at how will we operate the grid in the future with these variable intermittent renewable energy sources. So how do we work towards these high percentage of renewables? And that's from an engineering perspective. Very, very important piece of work. It doesn't tend to get talked about a lot. Then each year, AEMO brings out the Electricity Statement of Opportunities and the Gas Statement of Opportunities. This looks ahead 5 to 10 years and works out, are we likely to run short of something? Do we need more electricity generators? Do we need more gas pipelines? Do we need more gas to have been discovered and be sitting there in reserves? Again, they don't get talked about a lot, but they're very, very important documents. And then a fun one, which I like, is the AEMO Quarterly Energy Dynamics Report, which comes out obviously every quarter. And then there's usually a very good webinar which follows that, which goes through it. It tells us how we're going in terms of, let's look back at the last 3 months, let's work out what happened, looking at issues like negative pricing periods and how much frequency control was required, how stable was the market, and looks across all of the states in the NEM. So that's a really interesting report. 2 others that don't tend to get talked about much at all is the State of the Energy Market, again, an annual report, but it's put out by the AER, not by AEMO. Comes out every year. It's a fantastic reference book for international investors. I tell them, take this back with you, make sure you've got this link. And it tells them everything about the market in terms of generation, transmission, distribution, and the retail sector. So it tells them about all the retailers, who they are, how the retail sector works, gives reports on all of those things. It's a really, really good reference document. And then another very important document, which people usually only talk about when they're complaining about it, is the CSIRO Gen Cost report. New version came out for 2020, 2021. And this is the report that looks at things like the levelized cost of energy from all the different generation sources and also for batteries. So it is used as a very important input document for the Integrated System Plan. Back over to the left. As I said, that's been focusing on the electricity network, but that's not decarbonisation. The electricity network, the NEM, is probably 40% or something of the energy in Australia. And so there's another 60% that needs to be decarbonised as well. And so what decarbonisation documents, plans, ideas are out there that you can have a look at? This one comes up from time to time, but it doesn't have a huge focus, is the decarbonisation futures by ClimateWorks. ClimateWorks actually did this report back in 2014. And what they did in 2020 was go back to that 2014 report and do a review on it. So this is a really good report. And it's, if you're interested in this subject, it's one that's handy as a reference document and for looking at where we're going. You'll often hear people talk about, so in the future, will we have 200% renewables or 300% renewables or even more? And this was one of the excellent first pieces of work that was done, involving quite a lot of people from University of Melbourne and issued by the Energy Transition Hub. I was privileged to be at the launch of this report. And so what this does is it looks at, as we're going forward through these different sorts of scenarios, what the percentage of renewables might be as we proceed. And as I said, in the future, as we decarbonise industry and transport, so electrify transport and electrify the industry that at the moment uses oil and gas, then we end up with many more terawatt hours per year of renewables than what we have at the moment. So the current NEM at the moment is around 200 terawatt hours. And so there are quite a few of these plans out now which talk about a future with 400, 500, 600 terawatt hours of energy. But we don't yet have in Australia a total decarbonisation plan. America does. And this is a report I really like. It's just such a useful and interesting and information-full report. Obviously put out by Princeton University in December, I think December 20th of last year, 2020. And the public-facing report is a nice, simple 350-page PowerPoint. But it is easy to go through and it is easy to pick up later and use as a reference document. So this, as I said, is a total decarbonisation plan. It looks at decarbonising all the industry, all the transport sector, and the electricity sector, of course, by 2050. And the numbers in it are quite awe-inspiring and just quite staggering in size. Like the integrated system plan, it has multiple scenarios. So there are 5 scenarios. And as they say in the public presentations, Jessie Jenkins, who's often out presenting on this, none of these individual scenarios is what would be expected to happen. What would be expected to happen in the future would be a mix of them. And so they've used 5 different scenarios using quite different sorts of assumptions, very high renewables, constrained renewables, different types of constraints. And here is where you start to see how staggering some of the numbers are. In Australia, as I said, our electricity grid at the moment is 200 terawatt hours per year. And you'll see on the chart here that America at the moment is 4,000 terawatt hours per year. In other words, over 20 times the national electricity market. And depending on which scenario you look at for them going ahead into the future, the scenarios, as you'll see, are in the order of moving up to 10,000 or even 16,000 terawatt hours of electricity for an ultra high electrification of everything scenario. And so 16,000, of course, compared to the 200 terawatt hours a year in Australians NEM are just quite staggering numbers. And you can imagine the amount of renewable energy, wind farms, solar panels, etc. behind that. The numbers are just staggering. Interestingly, they did this 4th scenario here, one of the constrained ones. They looked at expanding the existing nuclear in America. So this sort of apricot colour, which is labelled here nuclear. And it's the only scenario where they increased nuclear. And so they looked at ending up with 3 times as much nuclear as what they've got at the moment. So a bit over 30% of the electricity output at that time being nuclear, instead of the sort of 10-12% that it is at the moment. So the scenarios covered a pretty significant range of options. This is one of my favourite charts in the Net Zero America, NZA, looking at the costs. And so here's a really nice simple chart that tells you a lot. How much do each of these scenarios cost? Well, if you look over to the left, it's a bit mind-numbing because they cost between $26 and $28 trillion. So we've moved away from billions and we're now into the trillions. But amazingly, these 5 scenarios ignore the reference scenario. That's a stick in the sand, stick your head in the sand and virtually do nothing. So all the scenarios of going forward only range between 26 and 28 trillion. So there's not much in it. It's 27 trillion plus or minus $1 trillion. So how big a number is that? What does that mean? Well, the GDP cost to consumers, to the economy of America, spent on energy per year is shown in the chart on the right. And when there were oil price shocks in the 70s and the global financial crisis in the first decade of this century, the GDP percentage spent on energy was in these high areas of 7 to 14%. All of these scenarios going forward are in the order of 4 to 6% of GDP being spent on energy. And so between the 26 and the 28 trillion, they're all very close to each other. Yes, the E plus RE minus is negative, which is the constrained renewables. That's the nuclear scenario. That one's shown as the cheapest there. Jesse points out that there are so many hundreds of pages of assumptions in these 5 scenarios. You only need to go through those 100 pages of assumptions and juggle some of them around a bit. And effectively any one of these can flip from the bottom to the top. So if you just consider that the average cost is around the 27 trillion, that's the important thing going forward. This is another important chart out of the 350, so I've only chosen a few, of course, which I think is important. And what it does is it says, as we progress through spending this 27 trillion, what has been my effective cost of removing the carbon from the system? A bit like the famous McKinsey curve, which you've probably seen, looking at the increasing cost of removing carbon as you go more and more into the individual sectors. And so in the first couple of decades, you can see that it's in this sort of $100, $150 US per tonne of carbon to remove it. And they're all the things that we can be doing in the next couple of decades. It does get hard. In the last decade, and particularly in the last 5-year period, you'll see there, the effective cost of removing carbon becomes much, much higher, multiple times higher. And this is highlighting that, yes, it is hard to get to that 100% total decarbonisation. And so I think this is a very important chart, and obviously it will change as we progress and move towards those particular years. It will change and hopefully it'll drop down considerably. There's a very famous lecture by Professor Ross Garnaut about the fish and the tail, and hopefully the tail will actually become smaller, the overall cost. These transitions are not simple, and they won't happen by just somebody saying we're going to have an energy transition. They require action by government and business and individuals. Everybody tends to look at government to make the changes that are necessary, and some governments of the world are doing this very strongly, and obviously state governments in Australia are doing this very strongly. But it must be done in a way, and the policies in there must be done in a way which are acceptable to business, because they're the ones that are going to actually have to come in and spend the money. And individuals need to make some changes as well. And that's some of the activities that were involved in the Yarra Energy Foundation. But the Net Zero America plan, as much as I liked it, it actually doesn't have an implementation plan yet. It's not locked in law. There's nobody actually driving it. There are some significant initiatives from the Biden administration recently that are starting to work towards the first steps of that. So this is why I like this one. This one is from National Grid. National Grid is effectively the AEMO in the United Kingdom. And interesting that they're the ones just like AEMO doing the integrated system plan here, it's National Grid in the UK that have done this decarbonisation plan in the UK. But I like this one because it is total. It's a total decarbonisation plan, and they've locked it in against carbon, the amount of carbon that they're going to allow to be emitted by the United Kingdom. And so this is what they took to COP26 this year in Glasgow, that they recently locked in June of 2021. They locked in carbon block number 6 for the period around 2035. So again, this has a series of different scenarios, just like the NZA and the integrated system plan. But these carbon blocks are locked in law. And so this is an amazingly impressive overall plan for how to decarbonise the United Kingdom and the carbon blocks that they will limit themselves to as they progress forward. Obviously, they need to still lock in the later carbon blocks, but to me, this is one of the best plans in the whole world, and that's why it's one that's worth looking at. As an engineer, I love Sankey diagrams, and this future energy strategy report has lots of Sankey diagrams. This is just one that I've picked out, which is showing you where they could be by 2050. And it answers a lot of questions in there. But as I said, this is a total decarbonisation plan. It's been difficult for them to come up with this plan. You'll see here over to the left, solar 81 units versus offshore wind 389. So their wind to solar ratio in this decarbonised plan, when you include the onshore wind as well, is around about something like 5 to 1, 6 to 1. So the intermittency of wind versus the intermittency of solar when it's 5 to 1 is going to be more difficult for them than what we have with our decarbonisation plans for Australia, where we can have a much more even amount of solar and wind. And so that will become important in future decarbonisation plans in Australia. So they've done pretty well to come up with that plan. And as I said, in June of 2021 this year, this went into policy. So they locked in that last carbon bucket, or that carbon block number 6, with locking in 78% fewer emissions by 2035, and that's what they took to COP26 in Glasgow last week. And so this is why I do like this plan. It's quite an amazing overall plan. The other big thing you hear people talk about a lot is the complexity of where we're going. So the energy transition, it is going to be complex. And so I've stolen this picture from Arup because I think it's just a wonderful picture of highlighting, yes, the future system will be very complex. Some people say this is too complex. They say this is too complex to be achievable, and it will just be too hard and it will fail, and we'll have to go back to coal or carbon capture or huge amounts of nuclear. So I think it's worth just thinking about that and whether we can manage that complexity. To do that, it actually wasn't always as complex as it is even now. So we often hear about frequency control services and AEMO matching the supply and the demand. This is a picture of the Latrobe Valley Control Centre, where they used to manage the electricity from the Latrobe Valley from each of the brown coal generators and gas generators coming up to Melbourne to go into the grid. And how did FCAS run in those days? Well, through this purple chair. So the red phone you could sort of say was FCAS, and the white phone you could sort of say was just load matching normal amounts of megawatts supply versus demand. This is where the system controller sat. He wasn't a computer, it was a person. There was a person here in Latrobe Valley Control Centre and another person in a chair in Melbourne. I don't know whether that one was purple as well. And normal calls were on the white phone. And when things got urgent, things like rapid changes in supply or demand, then the red phone was used, which linked the two people together. And they were then sending messages out to the individual coal generators to ramp up or ramp down. it wasn't all manual. So individual generators would have what we call very sensitive governors on them, a bit like the speed control in your car. So some of the generators would be at midpoint on their megawatt range, and their governors would be set to be very sensitive to try and maintain an exact speed of 50 hertz, or like you do in your car if you're setting your cruise control to be 100 kilometres an hour. When you look at the picture over on the right, you'll see there's no CRTs, no screens, there's no displays, no flat displays. That's because they hadn't yet been invented. So all of this was done with mimic boards like this, with just the little gauges that would swing from left to right. You also notice that it's a genuine 1970s picture, and you'll pick up with all the flares there. If you're really good at looking at the slides here, you might notice that guy on the left of this picture with the flares. Yes, that is how we used to dress in the 70s at work, even when you're a professional, and that is me. And you might say, wow, I had very long hair there. Well, I actually cut my hair to go and get that job. My hair used to be quite a lot longer, and I'm always looking for an opportunity to throw this picture into a PowerPoint, of course. So getting back to that question of, is it manageable, controllable and possible? The answer actually is not yet. EMO got a new boss recently, and Daniel Westerman came in, and in one of his first presentations back on the 29th of July, he actually said, to be honest, we don't yet know how to do it. And that's what some of the reports I showed you earlier, things like the renewable integration strategy, it's what's raising the questions on how are we going to do this? Is it possible to manage it? Can we get the computers we need to manage it second to second, day to day, as we progress towards 100%? I like the fact that he gave an honest answer, and that we're throwing a lot of engineers and a lot of computers at it, and we're working on this solution. But they're not the only ones. Many of you will have seen this picture. Can you imagine somebody saying to Elon Musk, well, the grid won't be controllable, just like they said to Elon Musk, after the rockets take off, the booster rockets are just dumped in the ocean and collapse and are destroyed when they hit the ocean. And he said, why? And he said, bring them back. I want to refuel them up. And 2 days later, I want them to take off again. No doubt people said, too complex, can't be done, too difficult. Those people wouldn't work for Elon for very long. The other big challenge that Elon's doing, of course, is the self-driving Tesla. And again, if you went into those meetings 5-10 years ago, there would have been many people in the room saying, too difficult, too complex, can't be done, can't be solved. We don't even have the computers to do it. When Tesla finds that they don't have the computers to do it, they just go out and they hire or steal the best computer designers in the world, such as this guy in the bottom left here. And then they work out that you need a computer where you need to get some chips, and in the top left corner, you need to get 15 kilowatts of electricity. 15 kilowatts, that's the maximum demand, say, in a house, into a couple of computer chips. And so they worked out a new way to do that by pushing the power in from the top of the computer chip all over it instead of from the side. So they completely redesigned the way a computer chip works. And then they worked out how to fill up a board with a whole pile of those onto one single board. And then they worked out how to pile all of those into racks and racks and racks and build effectively one of the top 3 most powerful computers on planet Earth. And what this computer is now doing, which is running, and the numbers down here don't mean anything to me, but they do to computer people as to how incredibly powerful this computer is. These are the computers that every time you grab the steering wheel in your Tesla, when you're on auto drive, and you grab it and take over control again because it didn't do something right, all of the information gets dumped down into this computer, and within 24 hours or a week or whatever, it's worked out how to make sure that that never happens again. And then it's constantly updating the self-driving software. So it's a problem-solving process and a learning process, and they're doing it with a computer that didn't exist a few years ago, and when they found they didn't have one, they just went out and built one. And so these are some examples. But how does that relate to the energy sector? Well, if you look at company X, so you probably have heard that the AEMO CEO, Audrey Zibelman, has gone back to America and is now working for Company X, which is a Google offshoot. And Company X is already looking at this in terms of energy. So they're looking at how to take all of that complexity we saw on that earlier diagram, how to absorb it all, just like a self-driving car needs to absorb, and then how to make sure that that can all be managed and controlled. And so you can imagine if the same effort is being put into this as it was into the Tesla self-driving, where we're getting to. So that was the presentation, and I hope you've enjoyed it, and I'm very happy to take any questions. Thank you very much.